Hello. So far we have dealt with two forms of general linear model. In the first instance, we looked at how a continuous response might be related to different levels of a categorical predictor, like the type of fertilizer. We then went on to look at how a continuous response might be related in some way to a continuous predictor, and we did this through fitting a linear regression model. General linear models assume that the world is structured in a certain way, and they summarize the way we assume the world to be. Statistics helps us test null hypotheses about the way we view the world. For example, whether the population mean level responses for each of the levels are the same, or whether the gradient beta in this linear regression model is equal to 0. In multiple regression, what we have is an extension of linear regression. We have a continuous response, an intercept, and a gradient with one continuous predictor, but then we can add more continuous predictors to our overall model. So y is a continuous response. The various x's here represent sizes of different predictor variables. They're all continuous. The beta coefficients refer to an intercept and then all of the gradients, each associated with these different predictors. And being a general linear model, we are assuming that the model isn't perfect and there is variability around that fitted model, which we assume to be normally distributed variability with a fixed variance, hence n0 sigma squared. One example, for example, might be aphid density and its relationship to the temperature in an area and also the crop age on which the aphids have settled. What assumptions are we making when we fit a multiple regression? Well, for any set of the predictors, we're assuming that the distribution of epsilon, the error term, is normal. We're also assuming that the variance of epsilon is the same for any combination of those predictor variables in terms of their sizes. We're assuming also that the observations on which the model was based are all independently drawn. We're not, for example, observing the same aphids or the same crop time and time again. And that we have the correct model, that indeed the world is like this, and we are therefore trying to do our very best to estimate the parameters at population level as judged from a sample. So here's what goes on in a multiple regression. It's rather similar to what goes on in a linear regression, except in this stage what we do is we find a plane or a higher dimensional surface which minimizes the sums of squares of deviations of the observed y to the predicted y. It's better to see it graphically here. So whereas linear regression fits a line which minimizes the sums of squares of deviations of observations to that line, here in this two-dimensional case with two linear predictors, what we're doing is fitting a surface which also is minimizing the sums of squares of deviations of observations to that model. Let's have a look at some sample data, and these data come from the excellent book by Graffen and Hales, and it's to do with the average maths ability of children of different age, years, and their heights. Now, first of all, in any analysis, I recommend very strongly that you plot the graphs out and you plot the relationships to examine the type of data you have in front of you. And here, having read the data, this is just what we can do. Now, if we look at the maths ability, we see that maths ability really does seem to increase linearly with height. And of course, we can fit a simple linear regression model here, where we have LM average maths ability by height, and with this we can actually identify the line of best fit. We can also test the null hypothesis that there is no relationship between maths ability and height, and we do this by saying ANOVA that fitted model. And what we can see here is that we reject the null hypothesis that there is no relationship between height and maths ability at population level. So linear regression has led us to conclude that there is a relationship, but of course that relationship doesn't have to be causal. And an obvious explanation might be that as children get taller, they also get older. So how does age influence that relationship? To understand how to disentangle the effect of one predictor on a response from another predictor on a response, we need to consider the various sums of squares available to us in an analysis of variance. And I'm going to introduce two here. The first one is the type 1 or sequential sum of squares, and the second is the type 3 or adjusted sum of squares. With the type 1 sum of squares, it's a hierarchical sequential system in which we try to look at the amount of variation explained by a predictor when everything above it in the list, i.e. all those preceding predictor variables, are statistically eliminated. However, by contrast, in a type 3 sum of squares, we try to identify the amount of variation explained by a given predictor when all other predictor variables are statistically eliminated. Now you might think that it's very sensible to use a type 3 in all cases. When we want to identify the role of A, we control for everything else. But there are, of course, a number of cases where that isn't what we want to do. And so really our choice of sum of squares depends on the nature of the questions that we're asking. But let's have a look at using a type 1 sum of squares, which is the default in R. Here is a multiple regression looking at the average maths ability and how it depends on years and height. And here we're plotting out the results from that analysis of variance. And what we can see from this is that years explains a significant variability in maths ability itself. It's the first listed, so we're not controlling for height. And yet height doesn't explain any significant variability in maths ability once you take into account the age of those pupils. What about in reverse? So we can look this type 1 sums of squares but actually fit the model in reverse. So first we're fitting height where we're not controlling for age in years, and then we're fitting years when we are controlling for height. This will give us our second analysis of variance, and we can see that we get a rather different answer when we put them in this way. Here height is statistically significant because we're not controlling for years, and yet years is still significant whether we control for height or not, as we can see with the first analysis of variance versus the second. So we're getting a picture here that the age of the pupil is really very important, and yet the height really is not. Height might appear as if it's significant, but it's only because you're not controlling for years. How might we do a type 3 sum of squares analysis of variance? Well, we can't do it in the default R, but we can if we load the package car, and here it is, I'm loading the library car, and using ANOVA with a capital A and asking to apply to that results object a type 3 sum of squares analysis. And this is what we get. Here, where we've got years controlling for height and height controlling for years, what we can see is the same conclusion that we had before, that everything is suggesting that these students are getting better at maths as they're getting older, but it really isn't directly related to their height. What about the fitted model? Well, we can ask to see the fitted model by simply going summary results or even asking directly for the coefficients of those results. But here is what R will give us out. Here is our various estimates, a very small gradient associated with the height, but a strong gradient associated with the years. And we can, of course, reconstruct our model here. There's the average maths ability against this intercept. There's the gradient here, and there is the gradient there. Now, you'll notice that fitting surfaces in terms of working out what the coefficients are of this fitted GLM is analogous to controlling for the effects of the variables. So the significance terms that we're seeing actually reflect type 3 sum of squares.